Well, I have to say, Molly, last week was both exciting and busy, thanks to the story that Venus may have life.
That's right. The detection of phosphine gas makes that an intriguing possibility. And you know that biosignature was found thanks to telescopes.
Right, we couldn't do astronomy without them. We're about to hear about the most famous telescope of all and the next generation of telescopes. But before we get to that, it's time to pass the hat.
That's because Big Picture Science relies on you, our listeners, to help us produce new episodes.
And now it's easier and more rewarding than ever when you support us on Patreon.
For only a few dollars a month, you can join like-minded BiPi-Sci fans, and in return, you'll be rewarded with bonus material, exclusive polls, thanks from us in the podcast, and more.
Just go to patreon.com/bigpicturescience. Takes only a few minutes.
In the Big Picture Science galaxy, every listener is a star.
So help us turn our stars into a galaxy. Just go to patreon.com/bigpicturescience. Thanks.
Thanks.
Things are looking up, or rather out. Why? Because of the launch of new space telescopes. So whether your interest is stars or dwarf planets, comets, galaxies, my favorite, the history of the early universe, or what dark matter or dark energy are, we have a telescope for you. Two of the most exciting instruments getting ready for launch will build on the discoveries of, well, the world's most famous telescope, and you can name that. It's Hubble. The exciting possibilities raised by learning more about how galaxies form and the properties of dark matter and dark energy may have us all saying, I need my space telescope. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute. Happy anniversary, Hubble Space Telescope, 30 years young. In this episode, the legacy of the instrument that fundamentally changed our understanding of the cosmos, and the two next-generation telescopes that will be joining it in orbit, one around the Earth and one around the Sun. This episode, Hubble and Beyond.
Now, I'm an astronomer, so of course I've spent a lot of time at telescopes, and I gotta tell you that if you spend a week or two at a telescope, it's like being in a monastery, right? Including the level of the food. But let me tell you why telescopes are so special. We want to know how the universe works, but we can't go there. We can't go to the stars. We can't go to distant planets, let alone to distant galaxies. But fortunately, information comes to us in the form of light. Telescopes allow us to study the universe by sending stuff to us.
So in that way, Seth, bigger telescopes are better because they collect more light?
Yeah, exactly. They're just like bigger buckets if you're trying to collect raindrops. But in the case of telescopes, of course, they're collecting photons. In other words, more light.
And in that way, telescopes are time machines. The more sensitive they are, the fainter the objects they can image, and the farther back we can travel in time.
Well, that's right, because light just travels at a finite speed. So if you look at the moon, you're seeing it as it was 1.5 seconds ago. That's not much back in time, so to speak. But if you're looking at stars, you might be looking back thousands of years. If you look at galaxies, you could be looking back many millions of years.
And so, in a way, this is a show about time travel. So let's talk time-traveling discoveries with our guests. We have all been aware of needing our space these days, but John Grunsfeld has been thinking about space for most of his life. He is a former astronaut for 5 space shuttle flights, a physicist with an expertise in astrophysics and exoplanets. Dr. Grunsfeld is known as the Hubble repairman for performing 3 out of the last 5 Hubble servicing missions. He has served as NASA chief scientist, and that means he was the principal advisor to the NASA administrator. And here's another interesting note. He is the only astronaut to climb to the top of Denali in Alaska, and we can only imagine he did this because it brought him a little closer to space.
Not because it was there. Meg Urey is the director of the Yale Center for Astronomy and Astrophysics. She was chair of the Department of Physics, president of the American Astronomical Society, and a senior astronomer at the Space Telescope Science Institute in Baltimore, which runs the Hubble Space Telescope. She studies the growth of supermassive black holes to understand how they evolved within galaxies. She's also devoted to making science accessible to the public and inclusive for women, something she shares with Nancy Roman, the noted astronomer for whom the Nancy Grace Roman Telescope, formerly called the W First Telescope, has been named.
Can I ask you, Meg, why put a telescope into space? I mean, it's harder to maintain it. There are a lot of disadvantages, and it's not because you're getting any closer to the objects you're photographing. Why do it?
Yeah. Although some people think that's why. No, there are several reasons. First of all, you're above the Earth's atmosphere, which blurs all images. So the images are much, much sharper. Second, the sky is dark. You don't have any nearby cities making a bright sky against which it's harder to see objects. So those are two big reasons. And a third is there are certain wavelengths of light that are not transmitted through the atmosphere. And so UV light, ultraviolet light, for example, can't be observed from the ground. So those are the big advantages of space.
When you look at the night sky, even from a clear space on Earth, say a mountaintop, the stars twinkle. Of course, there's a wonderful adaptation of a Mozart theme, Twinkle, Twinkle, Little Star. And having flown above the atmosphere on 5 space shuttle missions, when you're above the atmosphere and you look at the stars, they don't twinkle anymore. And that's our Earth's atmosphere and the disturbances in our upper atmosphere that are causing star images, points of light, to twinkle. And on a ground-based telescope, when you look through that atmosphere, as Meg says, it distorts it, it blurs that image. And so Hubble, being above the atmosphere, really can get those clear, crisp views.
Well, as we celebrate Hubble's 30th anniversary, I'd like to hear an overview from both Meg and John and also Seth. Seth, you're an astronomer, of what it's revealed to us about the universe.
Wow. I don't think you have time for the whole list, but I guess leading the list, first let me say, Hubble was designed to do a couple of important scientific problems, which it did beautifully, but probably the biggest hits are things that were not anticipated. And top of that list for me are the precise measurements of the expansion history of the universe using supernovae as standard candles. These are explosions of stars at the end of their lifetimes. And those, what John was just talking about, the ability to make very precise images without the blurring of the atmosphere was critical, because you need to separate these points of light that are the explosion of the star from the fuzzy light of the collective rest of the stars in the galaxy. And Hubble is amazing at doing that. So measurement of the distances to those stars gave a surprising result that the expansion of the universe is accelerating in the present day. And that implies the presence of something we call dark energy. It's just a name. It means we don't know what it is, which is some kind of new force, essentially, a new energy field. So that's my top list. John, where would you go?
Well, certainly, I think the discovery of the accelerating universe is certainly in the top 10, if not in the top 3. And, you mentioned that it's this new thing, dark energy. It's important to note that if correct, it accounts for 70% of the energy content of the whole universe. So it's a pretty significant thing. And what you said is absolutely correct. We don't know what it is. So that's a great mystery in physics and astronomy. I think one of the things that excites me a great deal these days, and when Hubble was launched, we didn't even know whether they existed or not, is the field of exoplanets, planets around other stars. And Hubble has been able to study the atmospheres of planets around other stars, which was never anticipated when Hubble was built, because of course we didn't know they were there. Now, it makes sense that other stars have planets around them, but it's a relatively new discovery.
Another thing that makes sense, but at the time was kind of a huge discovery, is that every single galaxy above a certain mass anyway, every single galaxy has a very massive black hole at its center. our galaxy, the Milky Way, has one. And this was something actually Hubble was designed to do, to look at the relation between what we knew were growing black holes and their host galaxies in a few rare objects we call active galaxies. But what was discovered was that basically every galaxy has one of these black holes, and that makes the growth phase of black holes part of the history of the evolution of every galaxy. So that was a huge discovery. And like the exoplanet one, John, that you just mentioned, it's something that in a way we just should have known. I mean, it's so obvious after the discovery, it's so obvious that that has to be true.
Okay, so Seth, what Meg and John have listed as the top finds of Hubble, the top discoveries, the discovery that the universe is expanding and it's accelerating in its expansion, exoplanets and supermassive black holes, and the supermassive black hole in the center of our galaxy. Can you add to that list?
Well, I can tell you my favorites. I mean, obviously, it probably won't compete. Remember that Hubble was launched to do the experiment that Ed Hubble tried to do. He was choosing his career path between, being a professional wrestler or being an astronomer, and he became an astronomer. But he was trying to, in fact, accurately measure the expansion of the universe. And Hubble went one step farther and found out it's not only expanding, but it's accelerating. Okay, but the thing that struck me most, I think, was when, I think it was the director of the Space Telescope Science Institute that runs Hubble, decided to take 100 hours and just look at one empty spot on the sky, and produce what's called the Hubble Deep Field Photo.
Certainly it changed our view of our universe in several different ways. And this is a central theme for the Hubble Space Telescope science, is that when you think about looking at the night sky, you think of it as points, little dots with a lot of black space around them. And that's because that's what we see with our human eyeballs. Now, there were big telescopes that looked at other objects, and in Edwin Hubble's early career, people used those telescopes and they saw these fuzzy objects, and they were sort of nebulous, and so they were called nebula. Once we got to space astronomy, and specifically the Hubble Space Telescope, where the Hubble can resolve individual stars in other galaxies, we started to see that the universe is a much more rich, and textural place. And as we then looked into this very dark point of the sky, a very black part of the sky that looked like it was devoid of anything, we looked back with Hubble for a very long time, and it was filled with galaxies that we could see all the different shapes and sizes. And, some of the older galaxies aren't as pretty as new galaxies, spiral galaxies. They're, they haven't fully formed yet. They're baby galaxies. We realized the incredible depth and richness of our universe.
Can I add something to that? I agree that the Hubble Deep Field really changed the way we do astronomy. And there's I like to think of it as astronomy for the people in two ways. One, by looking at this ordinary part of the sky, not distinguished by any particular bright object or known objects, it just did a census, the way, a statistical census of the universe with no preconceptions and no biases. The second way is that the director of the Space Telescope Science Institute at the time, Bob Williams, whose idea this was to devote his time to doing this observation, he made the data available immediately to the world. And that in turn stimulated a huge amount of research around the world in support of figuring out what all those objects are. And I think that was one of the first times there'd been such a huge unpre-planned collaboration internationally.
Not only that, all of the data that Hubble has taken over the last 30 years is available to anybody over the internet. Any of your listeners can get an account with Space Telescope Science Institute, the archive, and download Hubble data if you want to go look at your favorite object. If you want to look at Jupiter, you can download all the images and the scientific data, the individual data that Hubble has taken of Jupiter or a moon of Jupiter or of the Andromeda galaxy, whatever you want. And about half of the science papers now that are written by scientists come from people going into that archive of data and studying something that nobody ever thought of before and writing scientific papers.
We would be remiss if we didn't talk about some of the other amazing images that Hubble has produced, for example, that of the Orion Nebula. But I have a quick follow-up about supermassive black holes, if I may, Meg, just so we have maybe one less thing to worry about these days. If there's a supermassive black hole in the middle of our galaxy, now do we need to be worried that we are being slowly drawn into that? What does that?
Oh yeah, I hear you. Physics to the rescue, Molly. Physics to the rescue.
Please.
We are saved by angular momentum and the need for any orbiting particle, which you can think of the sun as or the Earth is orbiting the sun is orbiting the galaxy. The sun cannot fall into the center of the galaxy unless it loses a heck of a lot of angular momentum, which would take eons and isn't going to happen. There are many other ways we're going to end sooner than that. So no, we're not. In the same way that the Earth and the other planets orbiting the sun is exerting a huge pull on us, but that is not making us fall into the sun. It's just making us orbit the sun. It's exactly like that.
Okay, thank you. So physics to the rescue may be the new T-shirt that I make for myself. All right.
All is not safe, however. One of the discoveries of the Hubble Space Telescope is that the Andromeda galaxy, which we've always known is sort of heading our way, but it's going to make a direct hit. We've done very sensitive measurements now using the Hubble Space Telescope to see exactly in which direction the Milky Way and Andromeda are heading. And sometime in the next 5 billion years, or in about 5 billion years, the Milky Way and the Andromeda galaxy are going to collide. Now, individual stars won't collide, but there's going to be a lot of pulls one way and another as the two galaxies pass through each other and eventually may coalesce to form a much larger galaxy.
Well, John, let me just, assuage the fears of the listeners here, because when Andromeda slams into the Milky Way, it's just going to be good news, not bad news. It isn't that anything's going to hit you. It's just that there are going to be a lot more stars in the sky, right?
Well, it'll be pretty interesting because before they collide, the sky really will be filled with lots more stars. I mean, double the number of stars.
Well, Meg and John, one of the favorite targets of amateur astronomers is the Orion Nebula, also known as M42 for people who can't pronounce Orion. And you can see it here you can see it in both hemispheres, and it looks kind of fuzzy and red, and it's just in the sword of Orion. Hubble has also looked at the Orion Nebula. Why spend telescope time on it? I mean, it's pretty and all, but what's to be learned there?
So Orion, as probably many listeners know, is a birthplace for new stars. And it has been observed for a long time from the ground, and there are many beautiful ground-based pictures as well. What Hubble did is some kind of alchemy, because the image they put out, which are sometimes called the pillars of God, there's 3 sort of tall pillars of cold gas out of which stars are forming, and then the very hot new stars that have just formed are boiling away the gas on the surface, sort of sculpting them into these pillars. And that photo, I think almost more than any other single photo, made a huge impression on the public, on everyone who saw it.
And the individual colors that we see observing the Orion Nebula are the glow of individual atoms of carbon, nitrogen, oxygen, hydrogen. Not only does it look beautiful writ large, but as you zoom in, you keep seeing more and more detail. You see the filaments of gas being pulled by the stars. You see the effects, as Meg said, of bright nearby stars boiling off the gas. And as the gas gets boiled off and dissipates around these new baby stars, lo and behold, we don't see, just a new spot of light, but we see gas and dust and the star as a new solar system is being formed. And so one of the things that Hubble has taught us from looking at these star forming regions where baby stars are born are that not only are baby stars born, but baby solar systems are born at about the same time.
We'll hear more from astrophysicist Meg Urey and astronaut John Grunsfeld. But first, I have to say, that discovery that the expansion of the universe is accelerating was completely unexpected. Everybody, including Isaac Newton, figured that if the universe were expanding, it would eventually slow down. And it turned out it was speeding up.
The Wide Field Infrared Survey Telescope, or WFIRST, poised for launch next year, will reveal details about planets outside our solar system and about the nature of that stuff that is accelerating the rate at which our universe is flying apart, otherwise known as dark energy. Only now the telescope has been renamed for a pioneering astronomer. We talk about the Nancy Grace Roman Space Telescope next.
We continue to travel back through time in this episode of Hubble and Beyond on Big Picture Science.
You know, I found Meg Urey's point that Hubble was doing astronomy for the people quite inspiring.
Yeah, and with the concerted effort of a tiny percentage of Earth's population, that mission was launched that for decades has expanded humanity's understanding of the universe.
And with the help of a tiny percentage of the people listening to us right now, we can continue to produce this show for the foreseeable future.
It only takes a couple of bucks a month, and when you join us on Patreon, you get rewards.
Just go to patreon.com/bigpicturescience, select your level, and you will help bring BiPi-Sci to the public, including you.
And in return, you'll get access to bonus material, exclusive polling, thanks from us in the podcast, and more.
And that includes an expanded understanding of the universe.
So become part of our deep field of support at patreon.com/bigpicturescience. We really appreciate it.
Thank you.
We're framing this as a time travel episode because telescopes really are time machines, instruments that allow us to peer back at the birth of stars, the formation of galaxies, even the universe as it was shortly after the Big Bang. Now, while we're celebrating the 30th anniversary of the Hubble Space Telescope, it's worth pointing out that this is no retirement party. Hubble is still in orbit, and it's continuing to send back spectacular images. In fact, just recently, it imaged a small globular cluster, that's a ball of a few 100,000 stars, in a very nearby galaxy.
We're also looking into the future of looking into the past. The eponymous Nancy Grace Roman Space Telescope is set to launch in the mid-2020s as a successor to Hubble. Whether it can fill those very big shoes, or rather solar arrays, is also something we are discussing. After all, Hubble has been extraordinarily productive. So we continue listing the greatest scientific hits of Hubble and imagine what discoveries about the big puzzles in astronomy await us after the launch of the Roman telescope with our guests, physicist and former astronaut John Grunsfeld and astrophysicist Meg Urey. You know, we would also be remiss in our discussion about Hubble's legacy if we didn't talk about some of the trouble, the Hubble trouble. And now Hubble is considered the model of excellence, but, you know, it wasn't always so. And after the telescope went up in 1990, NASA discovered that the mirror had not been ground properly. Seth, I think you remember this.
Oh, I remember it personally. I was sitting there when in the astronomy department at a university when a guy busted through the door and said, "Shostak, Hubble is," and he used a word I can't say on the air. And I didn't even know what he was talking about.
Well, he was wrong, though, because of what happened next.
Eventually wrong, yes.
I have to say, I was at the Space Telescope Science Institute working there then at the launch. And as we saw the first images come back with not the crisp image we hope to see, but some rings around the crisp image. Let me slightly correct something you said. It wasn't that it wasn't made properly. It was made exactly, beautifully properly to the wrong figure. And that's because the testing apparatus that every step was checking the curve of the mirror, the testing apparatus was flawed in a way that was later reconstructed. People later understood that. The mirror itself was so precisely ground, but to the wrong figure. And I think it's a perfect illustration of the difficulties and the genius of science and engineering. Okay, so try to do anything new and difficult, and you will have to solve many, many problems. And in this particular case, it was a problem found after launch. After you've launched this big heavy mirror, you can't go up there and regrind it the way you could if it were on the ground. So what to do? And very clever people figured out ways to to basically make the optical correction, like a pair of lenses in glasses, to make an optical correction in the instruments. As a result, Hubble is, as good as a perfectly ground mirror would be today.
Well, thank you, Meg, for that correction, for a correction about the correction story.
So to speak, yes.
Well, the beauty of the Hubble Space Telescope is that it was designed to be serviced by astronauts, women and men in spacesuits, going outside and repairing things. And so by putting the corrective optics in the new instruments that they took up, they were able to take out the old instruments, put in new instruments with the contact lenses, and that completely took care of the optical issues that were caused by the misshapen mirror.
There were 5 servicing missions on Hubble, and you participated in 3 of those. If something breaks around the house, it's not difficult to fix it. I should put it this way. We're not risking our lives unless we're up on a roof, I guess, and not very nimble. We're not risking our lives to fix it. John, what is it like to work in the danger of space?
It is true that I like to fix things. When I was visiting my sister in Chicago a few years back over Thanksgiving, big family gathering, she mentioned her washing machine wasn't working. And so, of course, I set off to work and fixed her washing machine. And that's just what I like to do. And so doing that in space suits me just fine. But it is hard. You're in a bulky spacesuit. You've got big gloves that are like hockey gloves. And so you just have to learn how to operate power tools and screwdrivers and wrenches, and even handling tiny screws without screwing up, so to speak, in space. And it takes lots and lots of practice in the spacesuits and just in shirt sleeves, sometimes in a big swimming pool in Houston where we float. It's called the Neutral Buoyancy Facility, in our spacesuits and practice underwater to simulate space.
Meg, do you think he's captured that? Is he underselling it a little bit? Repairing the Hubble Space Telescope is like repairing your dishwasher, but with big gloves and a little bit more practice.
Yeah, maybe he's being a little humble there. I mean, there are 2 things. One, it's just super hard to do, right? For example, if you try to turn that screwdriver when you're in space, your body will go the other way. So the whole process has to be designed completely differently from what you would do on the ground, where, you can throw your wrenches and scream and shout. Up there, everything has to be very precise. And the second thing is, which I don't think astronauts talk about ever, is it's very dangerous up there. And people like me, total cowards, would never go. I mean, we're just, I wouldn't survive the launch. I'd have died of a heart attack. So they have a sort of cool, shall we say, that the rest of us just sit back and admire. And I have to say, everybody associated with Hubble is so grateful.
Well, if Hubble is now, if you will, the Maserati of space telescopes, why is it that, we're kind of phasing it out in favor of new telescopes?
Well, first of all, I don't think we're phasing it out yet. I hope not, because it's still a very powerful telescope. But there are things it can't do. And 2 things in particular. One is to go further into the infrared, for which there are special advantages to being in space. And that's represented by both of the next 2 telescopes. The James Webb Space Telescope, which is due to launch in a little over a year, goes much further into the infrared, has a larger collecting area, and will be able to see deeper into the universe. And then the newer and very exciting Nancy Grace Roman Telescope, formerly known as WFIRST, an acronym that is Wide Field Infrared Space Telescope. That telescope has a much wider field of view, much wider field of view than Hubble. It's a very similar size and sensitivity to Hubble, but we'll see something like 1,000 times the amount of sky in a given shot. So very wide angle. And therefore you can do the kind of survey we were talking about, the Hubble Deep Field earlier. You can do 1,000 of those in the same time you could do the original.
Well, maybe the 2 of you could explain why infrared. I mean, people think of infrared when they think of heat lamps, maybe, but why do you want a telescope that looks in the infrared? There's so many beautiful things to see in the usual part of the spectrum, the part that our eyes can see. John?
Well, there's a couple of big reasons. When we look into a region that's very dusty, say the region around a star that has some exoplanets orbiting that star, and we have dust in our own solar system too, but some places are even more dusty. The light that we see, that most of Hubble operates in, visible light, gets scattered and doesn't escape. So we can't see inside of these dusty places. Whereas the infrared light happens to be about the same size as the dust and is able to escape. And so we can peer through these dusty regions and see what's going on inside. So we can see perhaps planets around nearby stars. We can study those stars, especially the young baby stars where the dust hasn't cleared out yet, in much greater detail. The other area where infrared astronomy is incredibly important is, as we mentioned earlier, the universe is expanding. And light that was emitted, say, as very blue light or ultraviolet light in the early universe, as the universe expands, it stretches out that light. And as we see it here at Earth, it's now infrared light.
So we cannot see those galaxies in optical light. They just are invisible. Actually, they are not there. And so the early universe requires infrared telescopes.
And isn't it the case that, as is always true in astronomy, the most interesting questions being asked are always at the limits of what your telescope can do? So if you want to look way, way back in time, deep, deep, deep in space, it sounds like a George Lucas film. If you want to do that, you have to go to the infrared.
Well, that's
exactly
right.
I wonder if we could move on and just say a few things about the Nancy Grace Roman Space Telescope, because as Meg said, that is the new name given to the W1 telescope. And to introduce this telescope, we should introduce the scientists behind it. And Nancy Roman occupies a place that really bridges the past and the future. She's been called the mother of Hubble because she really spearheaded the development of the Hubble Space Telescope. And could you tell us, Meg, why was she so determined to see this telescope launch, and just remind us when she was working and urging people to launch Hubble?
Sure, yeah. So, well, of course, NASA was started, during the space race, and she was one of the very first, maybe the first astronomer. Certainly she was the first chief scientist at NASA. And I think she followed her own instincts, which is to say, not just that we should send people into space and explore a space environment, but we should be doing science in space. And she very early on promoted the first space telescopes, but then Hubble was conceived as sort of the great observatory in space, and she championed that. And of course, there were many, many scientists involved in making the science cases, in building it. But she was the person at NASA who just kept her foot on the pedal until it happened. And it took decades.
What would you say are the, just give me the top astronomical question that the Nancy Grace Roman Telescope may answer for us.
I think the Roman telescope will do two things. It's designed to do two things. One is to do a very deep dive on what dark energy is. The second issue is exoplanets, both the detection of exoplanets, but also the Roman telescope will carry new technology for a coronagraph to demonstrate the ability to image exoplanets that are very dim spots of light next to bright stars. It'll advance both those fields in particular, but many other things as well.
Finally, one thing that really strikes me about talking to you, Meg and John, is that I don't know what you were like when you started in your careers, but I get the sense that your enthusiasm for astronomy and space science probably hasn't diminished much. What drives that continued enthusiasm?
For me, there's, three big scientific questions that drive me. And it's, where did we come from? Where are we going? And are we alone? And they're questions that hopefully astronomy, the science of astronomy and astronomers can help answer.
I share John's interest in finding out those answers. I will say, I think there's no greater legacy that humans could leave behind than the knowledge we build up through the kinds of observations that Hubble and other telescopes do. We have figured out the world in which we live, and world writ large as you can, the universe. Many people who, if you say the word science to them, might kind of roll their eyes or yawn or perhaps not be interested. When you start talking about the skies and the stars and the universe and what's out there, I have yet to meet someone who yawns at that. And teaching students, that's where it's just so energizing.
Well, Meg Urey and John Grunsfeld, thank you so much for talking to us today.
It was a real pleasure. Always nice to talk to you, John.
Always nice to talk to you, Meg, and Seth, Molly, thank you very much.
Meg Urey is the director of the Yale Center for Astronomy and Astrophysics, and an astrophysicist who, among other things, studies the growth of supermassive black holes in order to understand the evolution of galaxies.
John Grunsfeld is a physicist and a veteran of 5 space shuttle flights. He is known as the Hubble repairman for performing 3 out of the last 5 Hubble servicing missions.
There is an understandable affinity astronomers have for telescopes, whether they be giant mirrored beasts or their even bigger radio brethren, the massive antennas I've used to study galaxies. That's why a story in the news this week was particularly disturbing for me. One of the many devastating forest fires burning here in California, the Bobcat Fire, encroached within 500 feet of the telescopes on Mount Wilson. Mount Wilson is just north of Pasadena, where I went to grad school. I never used any of those telescopes. Remember, I'm a radio astronomer, but I did go up to the mountain many times. The smell of the gear grease in those big white domes is familiar to me. And the Mount Wilson telescopes have been mightily important. The king of the hill is the 100-inch reflector, whose mirror took 5 years to grind and polish. In the late 1920s, astronomer Edwin Hubble used it to find some stars that regularly changed their brightness in a handful of nearby galaxies. And that told him their distance. What Hubble learned was that the farther a galaxy was, the faster it was moving away. The universe is expanding. As a society, we do our best to preserve important artifacts of our history. And I find it gratifying that thanks to the efforts of some dauntless firefighters, the instruments that opened our eyes to the incredible scale of the universe have been preserved as well.
You heard us mention the James Webb Space Telescope. Well, here's an engineer who helped build it.
We had a bolt, just your typical hex head bolt, and we put it into the satellite, and we realized, I want to say maybe 2 hours later, that bolt went into the wrong spot.
That's one project where you want to carefully follow the assembly instructions. Life inside a clean room, and what a new telescope can tell us about the birth of the universe.
It's Hubble and Beyond on Big Picture Science.
We've been talking about the big discoveries made and soon to be made by space telescopes. But imagine if those telescopes went into space with a loose wire or a loose screw, a slight manufacturing defect. Now, we've heard what happened after Hubble was launched in 1990 with a small aberration, a very tiny error in the shape of its mirror. Astronauts like John Grunsfeld, as you heard, went into space to fix it. Of course, it would be much easier to make those corrections on the ground. Actually, even better would be avoid making any mistakes in the first place.
Me being a younger engineer at the time, my main thing was don't break it.
Well, that was the mantra of Kenneth Harris when he was a project engineer on the James Webb Space Telescope at age 24. By then, though, he was a seasoned engineer, having started work at NASA at age 16. Before he left NASA Goddard Space Flight Center, Mr. Harris had worked on 4 more satellite missions and had landed on the Forbes 30 Under 30 list of innovators. That was out of a pool of 20,000 nominees.
I currently work for the Aerospace Corporation as a senior project engineer. On James Webb, I was the deputy integration lead for the IEC, which is basically electronics compartment box for the instruments on board.
We wanted to find out in what way, like the Roman Space Telescope, the James Webb Space Telescope, which, by the way, will orbit the Sun, not the Earth, will build on and enlarge on the discoveries of Hubble, and what it was like for Mr. Harris to help to build it. Here's what we do know. He spent most of his time in a one-piece coverall known as a bunny suit to integrate new instruments. That is to put them in and make them work.
Yeah. Bunny suits. Very, very cool to be in one.
Can you describe the bunny suit?
It's a full up and down gown that you're like, oh, maybe I should go to the bathroom before I get in this. And when you're on the floor constantly for, usually 5 to 6 hours at a time. You take breaks, but typically your full 8-hour day is in a bunny suit.
Is the bunny suit the term that the media use, or is that the term that the NASA engineers use?
So funny enough, the history of the bunny suit, I believe, came from IBM. I believe they were the first individuals to start using the bunny suit. We call it a bunny suit or a clean room suit at NASA. But also the media has adopted that as well. So I think they just like to refer to it as bunny suits. Actually, another funny story it's not really funny, but another story I like to share is if anyone's ever seen any of the old astronaut or space-like movies where we're dealing with engineers and scientists back in, let's say the 60s, 50s, 60s, for example, you'll see images of them in the clean room, but you'll see them without bunny suits on. Sometimes you see them, eating or drinking in the clean room. And it's just because it was at this time, individuals didn't know how sensitive these components could potentially be. And we realized that the worst case scenario end result is worse than just putting on a bunny suit and putting in these, guidelines in advance.
But there are no stories of hoagies or ice cream cones ending up in space on one of these things, right?
Oh, no.
You wouldn't be able to tell us.
Oh, yeah.
Okay. Now moving on to the engineering and the science. Now, you helped integrate the telescope. What exactly were you charged with doing? What did it mean you had to integrate the instruments?
Integration of instruments is basically when you're combining different components, different pieces of the satellite, plugging the instruments into the satellite. Like you just think about it like that, just like plugging your computer charger into the wall, basically, but on a much more sophisticated level. So my job was to make sure all the electronics for the instruments were correctly integrated to the satellite. You see, James Webb has the really big popular part that everyone sees, the quote unquote gold mirrors. That's what we call OTE, or the optical telescope element. There's a box right on the back of that. It's kind of rectangular in shape. And that's called ISIM, which is our integrated science instrument module. So we basically integrated those two things together and plugged the electronic components into them, thus giving data when we eventually fly it, or when it eventually goes out into orbit.
What was the technical challenge of integrating them? I mean, you made it sound like it's like plugging your computer into the wall. I have a feeling it was more challenging than that, but what were the challenges?
Me being a younger engineer at the time, my main thing was don't break it. I was really concerned about something going wrong, and there was a certain level of care you have to take with flight hardware in particular. And it wasn't my first time working on flight hardware, but there are a set of procedures we have to go through when we are assembling or putting together a Webb, or really any flight hardware. There was a time where we had a bolt, just your typical hex head bolt, and we put it into the satellite, and we realized, I want to say maybe 2 hours later, that bolt went into the wrong spot. And it's not as simple as just, getting your tool and taking the bolt out. You have to call contamination. You have to update the procedure. You have to get approval to remove that bolt. You have to find the correct bolt before you take out the old bolt. So, we had contamination come up there, like holding the vacuum next to the bolt as we're disengaging it. And that's to cut down on contamination that it can affect the rest of the satellite or the rest of the telescope in this particular situation. So, my main concern was A, learning as much as I could, but B, don't break it and don't mess anything up.
Are satellites, are they delicate? Do they break easily? It seems like they would be pretty hardy if they're going into space.
Yeah, satellites are typically pretty hardy. I wouldn't say that they're delicate, but I would say that they are sensitive. I will say sensitive.
What are the other instruments that are on James Webb?
So most of the instruments on James Webb consist of the different cameras and spectrometers. So it has near infrared, mid infrared, and a host of other instruments that are going to help us get all the data that we need for James Webb.
And what is the advantage of looking at the universe through infrared, whether it's near infrared or mid infrared?
The reason that we want to look into space in infrared as opposed to visible light is because of a concept known as redshifting. Redder wavelengths basically mean larger or longer wavelengths. basically we know that the universe is constantly expanding, meaning that it's getting larger and larger. So theoretically, that means that objects are getting further away from us, moving quickly away from us, which causes light to redshift. So this can mean that light would more likely fall into that mid and that near infrared that I mentioned earlier in terms of the instruments that are on James Webb. And that gives us access to see through dust clouds, to see through the gas clouds, and to see a lot further than, let's say, Hubble, for example, or any of the other telescopes that we've utilized.
So each instrument that you're using to look out into the universe collects different kinds of data. So the visible light is looking at visible light. We can all see that. And the infrared is collecting infrared, and that gives you another pattern of activity that you wouldn't be able to see with your eyes, that the visible light doesn't reveal.
Right. So the instruments on Webb are pretty sophisticated. Again, when you think of the concept of quote unquote looking back in time or looking back at the earlier galaxies, you want to make sure that all your bases are covered. So when you think of redshifting, you want to make sure that your instruments on board can capture it.
Now, the James Webb is supposed to be the successor of Hubble. It's one of the successors of the Hubble Space Telescope. In what ways does it carry on the mission of Hubble or advance the science of Hubble?
When you look at it just from a purely hardware point of view, you can obviously see the differences between them. Webb is significantly larger. Webb's mirrors are significantly larger, and it just has an overall different structure to it. But one of my favorite examples that I like to bring up is in the 1990s, Hubble imaged a picture that we know as the Pillars of Creation, or the Eagle Nebula. And it's basically a gas/dust cloud that are surrounded by a handful of stars. And this is seeing this particular snapshot of space in visible light. But Hubble has, we call it not so sophisticated now, back in that day it was sophisticated, infrared camera on it that enabled it to also see through that dust cloud. If you look at the Eagle Nebula visible photo next to the Eagle Nebula infrared photo, you can still see kind of the silhouette of the dust cloud, but you can actually see a much larger amount of stars. And that's kind of just like a small taste, a small, foreshadowing of what Webb will produce. We're looking for more of those infrared photos that allow us to see a lot more stars.
So, Kenny, one of the things, and you've alluded to this, that's incredible about telescopes is that they allow us, a telescope like Hubble and the James Webb, they allow us to look back in time. That's one of the things that we're doing. Can you say more about that ability of telescopes to take us back in time?
Yeah, sure. So I think before I get to that point, I need to talk about the differences between Webb and standard telescopes you have at an observatory on Earth, for example. So an observatory on Earth has a telescope, no matter how powerful it is, still needs to see through the Earth's atmosphere to see whatever it's going to see. James Webb is going to be launched into the L2 orbit, which is 1.5 million kilometers away. Orbits around the sun, and we're going to point it into the quote unquote darkness of space, which is, away from the sun. It's cold, and it doesn't have a lot of those light interferences. So you don't have the light from the Earth, you don't have the light from the moon, you don't have the light from the sun and other, bodies that are typically in the way when you have telescopes either on Earth or ones that orbit Earth, i.e. Hubble. So the thing about Webb is that it'll be able to have none of those interferences. And because it doesn't have those interferences, and B, because of the set of instruments on board with it being able to observe longer wavelengths, it's thus able to see stars, galaxies, and light undisrupted at a much purer sense. So when we think of seeing and understanding light at a deeper sense, you want to see the light before the galaxy or before space starts to expand. So by being able to see wavelengths at a longer wavelengths before redshift happens, you are thus seeing back, quote unquote, in time to the original state of light or original state of a galaxy. And that's kind of what sets them apart from other telescopes. That is literally the concept behind the Webb telescope, or calling it a time machine, or, some say a time telescope. It's essentially you personally are not traveling there per se. So you are not traveling through time, but what you see is a pure or an initial state of light.
So what are the big questions that the James Webb Space Telescope trying to answer?
What did some of the first galaxies actually look like? Again, when you're thinking of this quote unquote time machine or this time telescope, I guess, that can look back and see some of the first galaxies, we want to A, understand what they look like, B, understand how they began to form, how they were created, and give us a better understanding of the universe as a whole. When you think about the telescope, it is designed to see very faint objects. So if you compare it to Hubble, about 10 to 100 times fainter than Hubble, we want to be able to utilize that technology, again, just to understand the universe in its very, I'll call it its infant stages. That's kind of the concept behind James Webb. It's a time telescope of sorts.
Well, finally, Kenny, I read that you were on the path to, or one of your dreams is to become an astronaut. Is that still true?
Oh yeah, very much so. I I talk to my mentors pretty often about this, but kind of something that I've shared with them is that being an astronaut for me is really a plan B, I'll call it. It's definitely something that I strive for. It's something that is in my heart. But at the end of the day, I will continue on my path to do these satellites, to do these telescopes, to integrate, build XYZ. And if that leads to the astronaut program, so be it. But if it doesn't, I'm going to continue to put my heart into, every mission that I do regardless. So that's definitely a dream of mine, but I do intend on staying the course of, being the best engineer I can.
So plan B is to go into space and plan A is to be an engineer here on Earth.
Yep.
Kenny Harris, it was a delight to talk to you. Thank you for chatting with us.
Definitely. Thank you so much for having me. It was a true honor.
Kenneth Harris is a senior project engineer at the Aerospace Corporation.
Well, it's big picture time. And what is the big picture of the legacy of Hubble and the two new generation telescopes that are going to join it in orbit?
So, 150 years ago, the big question was, what makes the stars shine? Nobody knew. We figured that out in the 20th century. But now in the 21st century, we can ask questions like, well, how do they form? These new infrared telescopes will tell us that. But not only how do stars form, but how did the early universe form? How did the Big Bang turn out to produce galaxies, stars, planets, and us?
We could not do the show without the far-reaching abilities of producers behind the scenes. Senior producer Gary Niederhoff and assistant producer Sarah Derwin, thanks to both of them. I am executive producer of Big Picture Science, Molly Bentley.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit education and research organization that investigates, among other things, the formation of stars. I'm the Institute's senior astronomer, Seth Shostak. Also, a big thanks to our listeners and Patreon supporters.
The episode of Big Picture Science you've been listening to is called Hubble and Beyond.